Hello and welcome. Today we are going to dive into the fascinating physics behind pretty much every note you've ever heard from a guitar, a violin, or a piano. We're going to unravel the mystery of something called a standing wave.
I mean, really think about it for a second. When you pluck a guitar string, you get this clear, sustained tone. But why that specific pitch? Why not just a dull thud or a jumble of random sounds? Well, the answer lies in a very, very special kind of wave.
And here is the paradox that makes this whole thing so cool. The sound is created by a wave that, for all intents and purposes, looks like it's standing perfectly still. Yeah, I know, it sounds completely impossible, right? But believe it or not, that's the key to everything.
So how on earth can a wave stand still? Well, it's not magic. It's actually a beautiful phenomenon of physics called interference.
Okay, so picture this. You've got a wave traveling down a guitar string. When it hits the end, it reflects and travels right back. So now you have two waves, one going forward, one coming back, and they're moving right through each other. And that right there is the crucial point. You see, a standing wave isn't actually a single wave moving anywhere. No, it's the pattern that emerges when those two waves interfere, when they add up and cancel each other out in this very specific, stable way. It's a phenomenon that is purely about interference.
And you can see exactly what that result looks like. Instead of a wave that travels left or right, you just get this fixed, pulsating shape. Some parts of the string are moving wildly up and down, while other points they're completely still.
Now, these points of stillness and maximum motion are so important that, of course, they have their own names. So let's break them down.
So, on one hand, you have what we call nodes. These are the points of perfect cancellation, total destructive interference, where the string doesn't move at all. And on the other hand, you have the antinodes. These are where the waves add up perfectly, creating the biggest possible vibration. It's this constant, predictable pattern of stillness and action.
To make this even clearer, let's just imagine an amusement park ride called the standing wave. If you wanted the most thrilling experience, where would you choose to stand?
You would absolutely want a spot on an antinode. That's where you'd be flying up and down with the maximum possible amplitude. The nodes? Well, that's where you'd stand if you just wanted to watch everyone else have all the fun. Okay, so we've got this stable pattern of stillness and action. Now let's connect this idea all the way back to our guitar string and see how it actually creates music.
So the simplest possible standing wave, what physicists call the first harmonic, or n equals 1, has just a single antinode in the middle and two nodes at the ends. This pattern vibrates at a very specific rate, the fundamental frequency, and that is what creates the main musical note that you hear.
But here's the thing. A string can vibrate in more complex ways all at the same time. The next possible pattern, the second harmonic, has two antinodes. This creates a higher-pitched note, an overtone, that vibrates along with the fundamental to add richness and character to the sound.
And the pattern just keeps going. Here's the third harmonic with three antinodes. A real vibrating string is actually producing many of these harmonics at once. But here's the key. Only these neat whole number patterns are physically possible because the string is fixed at both ends. It literally cannot vibrate any other way.
And this brilliantly illustrates the answer to our original question. A guitar string produces a musical tone because it can only support these specific standing wave patterns. It can't just vibrate any old way. It has to follow these rules of harmony.
This is already incredibly cool, but the principle of standing waves goes far, far beyond just making music. So you might be wondering, does all this fascinating physics just end with music? Not at all. The very same principles that make a guitar string sing are at play in some truly surprising places. I mean, think about the column of air inside a flute or an organ pipe. That's a standing wave. The antennas that transmit and receive our radio and Wi-Fi signals, they are designed around these exact principles. It even shows up in medical technology like ultrasound, which uses wave reflections to create images of what's inside the human body. And all this reveals one final crucial difference. A regular traveling wave, like a ripple in a pond, it carries energy from one place to another. But a standing wave actually traps that energy. It confines it right there between its nodes. The energy is there, vibrating furiously in place, but it isn't actually going anywhere. Now I want to leave you with one final thought. Something that takes this concept from a guitar string and connects it to the very fabric of our universe. This fundamental idea
That a system can only vibrate in certain, specific, allowed patterns has a really profound name in physics: quantization. Just like our string can only have the first, second, or third harmonic and absolutely nothing in between, many things in the quantum world are restricted to specific, discrete energy levels.
So the next time you hear a single, clear note from a musical instrument, remember what you're really hearing. You're hearing a physical manifestation of one of the deepest rules of our universe, that nature, from music all the way down to atoms, often plays by a set of very specific, quantized rules. And it all starts